Hi everyone, and welcome to today's session of Towards Trustworthy RISC-V processors for safety critical applications. My name is Salaheddin Hetalani. I'm Field Application Engineer at Siemens EDA. Today's presentation starts with a brief introduction about OneSpin history in the processor verification domain, followed by an introduction of the RISC-V processor core verification app, the main flow, supported features, and how to add custom extensions. Then we will get to know what kind of bugs the app is able to identify, going through two of the cores where it was applied, and finally hint a bit about the underlying technology. OneSpin has plus 15 years of experience in the processor verification domain. We've got many papers and presentations presented by our customers in conferences like DVCon or TAC, and recently related to RISC-V in the trust domain by Adaptive in GOMAC Tech 2019. The development of the processor core integrity solutions, either on the core level or the integration level, is ongoing, supporting new features. OneSpin is an active voter in the RISC-V International Organization and an active contributor in the Open Hardware Group, verifying many of their cores like CV32E40P, for instance, as well in the German-funded project Scale for Edge. There is a broad range of end customers adopting our solutions. And here's an example of one of the bugs that we were able to identify in a processor core where a division result wasn't written back to the register file. So what happens here is that the division instruction is propagating through the pipeline, and once it leaves the write back stage, it marks its result as pending. After some time, there is a load that is fetched from a misaligned address. And at the memory stage, this misaligned load is cancelled. However, its data cache isn't. By the time the pending division result arrives, it is accepted as there is no conflicting register file write in the pipeline. However, the conflicting data cache read data is written instead to the register file in case of a cache hit. And there are countless other possibilities for similar bugs that require many conditions to be true at the same time to be triggered. So how do we catch such bugs? Here comes the OneSpin app RISC-V processor core verification. The main characteristics or features it brings are, first, a factor of 10 verification speedup compared to simulation. If we were to set up the test bench that is time consuming and start our verification. It has optimized formal engines, allowing us to achieve unbounded exhaustive proofs in a short time. And it systematically detects bugs, allowing pinpointing issues and quickly fixing them. It has high degree of automation with the automatic microarchitecture extraction, mainly CSRs, and the automatic assertion generation. There is as well a built-in disassembler annotation, allowing users to know at any point in time what kind of instruction is being executed in the pipeline. The nature of the verification is exhaustive and complete, as it's based on the gap-free methodology that is unique to OneSpin. We are gonna introduce it in the last section of this presentation. Thus, achieving 100% functional coverage is possible, where we are sure as well that there is no additional functionality implemented in the RTL. So our RTL is doing only what it's supposed to do and nothing else. ISA and privileged ISA compliance is a side product of such verification. So it's really not the main focus of this app. The flow starts with the core RTL implementation. Based on it, automated design analysis is carried out such that architecture and microarchitecture details are extracted and stored in a database. By architecture, I mean the extensions that are implemented in the core. And by microarchitecture, mainly it's the CSRs that are as well there in the RTL. Then this information is populated into the GUI so that users can navigate them and extend them by implementation info. As an example of such information to be provided, for instance, the signal that holds the read data from memory. For the app to extract this signal or this information, it needs to know what is the memory protocol that is implemented. So for now, it's not generalized enough to do such extraction. That's why users need to provide this information. And for that, they can do it in two different ways, either using the GUI or in a scriptive way using JSON file. Same in case there are custom extensions implemented. As we will see in the next slide, we can add them in straightforward way using the GUI, for instance. So once this information is provided, our database is updated, and we are ready to generate assertions. Once we generate the assertions, then we can read the verification files, mainly the checker file, and we are ready to run the assertions in the tool to either get counterexamples or get all our assertions to hold. And in that case, we are sure that we achieved 100% functional coverage. Of course, as well, we can export the coverage information to any simulator of our choice, as we will see as well in the last section. So, Apps GUI is divided into two main parts. The ISA part, instruction set architecture part, where you can navigate all the extensions that are there, register width, number of counters or PMPs, and the microarchitecture part, where we can explore information about the pipeline or memory interfaces and so on. And there's specific section for custom extensions. The extraction starts by pressing on the button extract from design. Then all information extracted is going to be populated into the GUI. And as a user, then you can extend or assist the app by providing the core specific information or your custom extensions. Once we do that, our database is updated and we are ready to generate the assertions. So how to add custom extensions using the GUI is just a matter of specifying the name of an instruction, for instance, how it is decoded based on the RISC-V ISA standard, how it is disassembled so that we know while debugging issues what kind of instruction is being executed, and how this custom instruction is supposed to be executed. The execution here is based on subset of the SAIL language, which is the formal description language adopted by RISC-V International. So it's really straightforward to add custom instructions. Same in case we would like to add registers or register files. And we do support multiple source or destination registers. As you can see here, this field is for both the first source register and the second destination register. Standard extensions modeling is also based on a JSON database with sale execution. So we use the same modeling for both standard extensions or custom ones. And now, if you have the question, I have an extension and I would like to know if it's supported by your app, and if not, when it can be supported. So the answer to that is that all standard extensions are supported, but if there's an extension that doesn't have sale model released yet, then we don't support it. Now, once this sale model is released, our support comes after some time based on customer interest. And we did that for the bit manipulation extensions, for instance. All these extensions got supported immediately after their sale model was released. And now we are in the process of supporting the vector extensions. We are just waiting for their sale model to be released as well. Once we generate the assertions and we read the checker file, we get all the assertions to be shown in the tools GUI. So the assertions are grouped based on their extensions. Here, as you can see, we've got many assertions verifying all instructions of the integer instruction set extension, the I extension. As we can see here, there are many assertions for the multiplication extension or the compressed one. In case you've got custom extensions as well, they will have their own assertions. We've got many assertions for exceptions based on the pipeline stage they might occur in. Same for interrupts. And for this kind of configuration, we have only 27 assertions generated. So it's really clean. And we do provide many reference cards. Here is one example of a mapping of the app assertions to what instructions or exceptions are covered by them. So for each assertion, we will know that, okay, this assertion rv32i.arithmetic is verifying all these instructions in one go. We did apply the app to many cores. Here's the list or the types of bugs we were able to identify, taking into consideration only these 3 cores. And we will talk about the first 2 in the next slides in more details. We've got many situations of illegal instructions being executed as if they were legal, where the core was supposed to throw illegal exception for them, but it didn't. And of course, many situations related to CSR, access rights, privilege, and so on, where there were pure violations. Counters that were incremented where they weren't supposed to be incremented. Many situations related to undocumented functionality, like having undocumented instructions or CSRs, and the hardest that are about misbehaving pipeline or instruction. The simplest you can think of in this category is a forwarding issue, for instance. And these kind of bugs are usually tricky because they require, again, many conditions to be met at the same time to be triggered. So the Rocket core is 64-bit core. It has the configuration RV64GCZICSR G here stands for I, M, F, and D. So it has 2 of the floating point extensions. It's 5-stage single issue in order pipeline with virtual memory address space, 3 privilege levels, machine level, supervisor level, and user level, out of order termination for long latency instructions like division, and branch prediction and replay mechanism. This core was verified and taped out multiple times, and we were able to identify 8 issues in it. First one is the bug we introduced in the beginning of this presentation about the division result. Other bugs were about undocumented non-standard instruction. That was a seize instruction executed as if it's legal. Undocumented non-standard CSR that was read back as 0. And lastly, a debug mode only instruction that was executed outside the debug mode, which is as well illegal. Of course, you can navigate this link to have more detailed information about all these bugs. The second core, before that, performance-wise, it took us less than 5 days to set up the verification environment and less than 10 minutes to run each of the properties. A total runtime of less than 2 hours is enough to get convergence for all the properties, and this is sequential runtime, meaning that if we were to run the properties in parallel, achieving a better time is possible. The second core that we consider here is the open hardware core, known previously as RISC-V. Now it is CV32E40P. This core has this configuration. It's 4-stage, single issue in order pipeline with some support of privilege specification like user mode and physical memory protection. And it has many custom instruction set extensions as well. A total of 24 issues were found in this core, like having wrong PMP computations, where PMPs beyond the first match were searched. A wrong floating point instruction result that was written to the register file, and this was a forwarding issue. Or illegal instructions that were retiring, where they were supposed to not retire. A closer look on one of the bugs of this core was caught by our CSR assertion. So this assertion verifies the 6 CSR instructions, and we got the fail after 5 minutes. In the counterexample, we see here that certain CSRs, like machine interrupt enable and mStatus, are set to certain values such that we know that interrupts are enabled. And right after the interrupt is taken, here we know that interrupt is taken because mcause CSR holds this value 23, right? We have our CSR instruction, but this CSR instruction is considered illegal. It throws illegal exception. We know that because mcause holds the value 2, and machine exception PC holds the same PC of our instruction. So why this is the case? Why this legal instruction was considered or is considered here illegal? The reason for that is that there is unknown instruction or illegal opcode at the same time where the interrupt was taken. And this illegal instruction was confused by our instruction. So we reported this bug to Open Hardware Group. It got confirmed and fixed, and we were able to achieve exhaustive proof within 10 minutes. Instructions are mapped to the operational assertions principle. So what does that mean? The overall specification is broken down into a list of operations such that this list of operations forms complete specification. You can think of an instruction being executed in the pipeline as an operation. The transition of this operation is triggered by some inputs and architecture registers. By architecture registers, we mean register files like the integer 1 or floating point 1 and the CSRs, control status registers, and the program counter. So we know that once this add instruction is executed, we observe some values on the inputs, right, and the architecture registers. So once this is the case, then we know that by the end of this operation, outputs and architecture registers should hold certain values. So the operation defines the values on these outputs and the new values for the architecture registers, such that these new values would become the current values for the next operation. That might be another instruction or an exception and so on. And the tool would automatically consider all the sequences of operations and all combinations of trigger conditions. So we don't need to worry about that. Now, how do we capture these operations formally? Is by means of operational assertions. So system Verilog assertions that are based on TIDAL, which is the assertion library by OneSpin, to allow capturing timing diagrams specification in a straightforward way. For instance, here we are saying that, yeah, at this time point, we have an add instruction and we are, as a pipeline, we are in a certain state. So this should imply that by the end of this operation, and this is very simplistic expression of this operation, right? The destination register should hold the result that we are expecting, for instance. So we capture formally operations by means of operational assertions. And this is a key enabler for gap-free verification. As we've seen, we need only a few number of these operational assertions for instructions, exceptions, or interrupts. Gap-free itself allows or enables developing executable specification in the form of assertions. So it proves that this executable specification has no gaps or inconsistencies. You can think of this specification as a set of properties. So once it proves by running many checks, once it proves that this set of properties has no gaps or inconsistencies, then it proves it against the RTL. It proves that they are functionally equivalent, and thus we would be able to achieve 100% equivalence between the specification and the implementation. And if that is the case, then we demonstrate that there is absence of box trojans or ambiguities. RISC-V processor core verification app as well make use of OneSpin's FPU app to verify floating point extensions, making sure that we calculate the results of these floating point instructions correctly. And this app supports half, single, double, and custom precisions, all 5 rounding modes and 5 exception flags. In terms of coverage, there are 2 main products to talk about here. First is Quantify, and second is the portable coverage. So let's start with Quantify. We run the set of assertions on the RTL and we prove them, right? And we would like to know for each line of the source code if it was covered or not, and if it was covered, which assertion did cover it. So quantify that does mutation coverage answer that question, and as well it let us know what parts of the source code are dead, which parts that are unreachable. So if you would like to export quantify coverage, we can use one of the portable coverage apps, like, for instance, Verification Coverage Integration app, which exports quantify results into any simulator of our choice. If we were interested only in the assertion results, so we run a set of assertions and we get hold or fails, and we would like to annotate these assertion results into our verification plan, then we can use Verification Planning Integration app. And finally, if we were interested only in accelerating coverage closure by exporting the lines of codes that are unreachable. So for that, we can run other OneSpin app that is called AutoChecks to identify dead codes or unreachable FSMs. And then we can run Coverage Closure Accelerator app to export these locations to our simulators so that we don't target them in our simulation verification. So to summarize, OneSpin's RISC-V processor core verification app brings more than 10 as a factor of improvement on the verification setup and runtime, where you really don't need to worry about writing a test bench, generating stimulus, and so on. The tool is going to do all of that for you. It has high degree of automation, extracting microarchitecture details, which as well enables automated verification of generated core from common specification. It makes it easier to verify custom extensions. If you were to pick up a core from an open source and add your custom extensions, then for each added instruction or each added custom functionality, you need to rerun the verification from scratch, right? So with the automation the app offers in terms of the microarchitecture extraction, this makes it really way easier. The nature of the verification is exhaustive and complete. As we've seen, applying the app on many of the cores, we found a lot of serious bugs. And it is a superior and unique solution, leveraging OneSpin's expertise and the unique interval property checking and gap-free verification. In the end, I would like to leave you with this quote from one of our customers. Thank you for being here today.